This is the 5-3 notes for Calculus 1. This is the section when we start to progress towards being able to find the result of a definite integral. More specifically, how to find the exact area under a curve. And by area, I mean net area. So before we do that, though, what I want to do is I want to define what's called an area function. So basically, in terms of integration, an area function is a way to accumulate area under a curve. So we use this formal definition in the beginning to represent what the point of what we're trying to do. But basically, you have a function like this, and you start at some value of a, and you go to any value, constant value, then basically you can accumulate area by doing so. So what I did basically was I set up a little scenario down here to show you how this works. So first, I have a typical XY graph where the Y represents the area accumulated, and X represents where you are on the X-axis, of course. So when you look at our first graph here, basically what we're doing is we are going from A to B. So we're replacing the X. On the X-axis, we're going to the value B, which is right here. So if we go from A to B, we're essentially accumulating the area under this curve right here, right? So that means the area is going to increase. So we don't know what that is, basically. But that means, and so what happens is in the graph down here, the bottom, currently at the point B, we have a certain amount of area that we have accumulated so far, which represents the area right here. Okay, let's say we go further to the point C. So now we have this much area in the same graph accumulated. So basically we've filled in this piece in here, right? So we would expect, obviously, that the area would again increase. So at C, we have even more area. How much area that is over here. There's no numbers. It doesn't really matter what the numbers are. Now, they do a little clever thing here by saying, okay, well, what if we went from A to C, but then we went from C to D and we added that together? In other words, go from A to D. Now, the graph seems to be tailing off. So instead of continually rising, now all of a sudden the graph is decreasing. So we're back down to here. Why is that? Because we know that the area in here is what contribution to the net area. It's a negative contribution. So now the net area of this graph, so we want to be really specific, net area is now decreasing because we're there. Now, basically this graph will keep on going because this line will keep on going, and as we accumulate, we're going to continue to put a negative spin on the area, but basically what this shows you is that an definite integral allows you to accumulate area as you go, and we call that an area function. Just remember, though, just from our previous section, that there's no area at A itself, which is why we start at A0. Okay, so what this does is it just further shows a sort of a more involved approach about accumulating area under a curve. So what this does is this leads into a very famous theorem of calculus, maybe one of the most famous ever, called the fundamental theorem of calculus. Okay, so the first part of the theorem is not really so much that we use in application, but I can just summarize it real quick. Basically, if you look, first of all, it states the area function, right? So we basically know that if the function is continuous on some interval a to b, then we can accumulate area using a definite integral. So that is the first statement. But the second statement, which is right here, the second integral equation here, is basically saying that if you take the derivative of an integral, you're going to end up back at the original function. So we've already talked about before, that's what makes an antiderivative what it is, in the fact that if you take the derivative of the antiderivative, you're going to end up right back at the original function again. So this is just more about definitions and theory than anything else. The key part of the theorem is part 2. So this is basically one of the most important things that you're going to learn in this class. And what does it state? It states how to actually solve an integral. In other words, how to find the actual exact area under a curve. What does it state? As long as your function is continuous on the interval, then being capital F is the antiderivative, the definite integral from a to b of f of x is the equivalent of taking the antiderivative and evaluating at b, taking the antiderivative and evaluating at a, and just subtracting them. It's an incredibly simple yet powerful concept that you'll be using for the rest of this class and most of Calc 2, if not all. So what we're going to do is this whole lesson is going to be based on making sure that you can follow the definite integral process towards finding the exact area. So this process I expand a little bit because you'll see that I've put, so this formula here, so what I've done is I've put an extra step in here, which is also an incredibly important step that you have to know. It's not in the theorem, but it is part of what you're going to have to be able to do. So let's say you're provided with a definite integral. So what you do before you get to this step is you take the antiderivative, and then this bar symbol means to evaluate. So what this says is if you're taking the definite integral of some function from a to b, then that's equivalent of taking the antiderivative of that same function and evaluating from a to b. Well, what does that mean? That essentially means this. So this is an in-between step that you will include in every single integration problem that you do, and this is how you find a definite integral and the area under the curve. So obviously we went through the entire Riemann sum process, right? So the Riemann sum process is all about approximating area. So what this does is this essentially replaces that process, because why would you approximate when you can find the exact area? So you might say, well, why did we learn about the Riemann sum then? Well, as you remember, the definition of a definite integral is the limit of the Riemann sum. So you had to learn it for conceptual reasons and how to do it, and you'll still have to do it on an exam, so to speak. But from now on, what you're going to be concentrating on is finding these definite integrals, and oh boy, we're going to be doing a lot of examples of it. Alright, so we're going to start in on some examples. Basically, the definitions are going to be something like evaluate the following integrals, something like that. They're not going to tell you what to use, but this is a nice little hint that we are using part 2 of the fundamental theorem of calculus, which essentially is this. So this is how we do every problem. I'm going to show you the steps. Note that the picture again is provided only for lessons. It won't be in exam situations because it is valuable for you to see what type of area you get, where is the area, how much area, all of that is very valuable. So look at number 1. We are trying to find the area under the curve 60x minus 6x squared with respect to x from 0 to 10. Okay, so just a quick look at the picture. So we are going from 0 to 10. We have right now the graph of this curve right here. Right? This curve is our function, 60x minus 6x squared. And by asking you to do this, all we're doing is finding this area. That's it. We're finding that exact area under the curve, and that's the point of what we're doing, basically. So how do we do that? Well, we have to follow that fundamental theorem of calculus rule and work through the problems. Now, you're going to find that in the beginning problems are probably going to be very easy for you because there's no fancy rules. Well, we'll get to that in due time, because, but we'll just start with the easy stuff. So what do we start with? Well, the next step, which we'll do down here in this process, once you have your definite integral, let's get rid of all this here so I can go back to the note-taking. So our next step is to go to this step. So what is this step? It says take the antiderivative and then evaluate at the same values of a and b. Okay, so what we need to do is we need to take the antiderivative of this. So this right now is f of x. We need to find capital F of x. So what is that? Well, we take 60 as our constant and then we integrate, or in other words, find the antiderivative of x. Well, what's the antiderivative of x? It's x squared over 2. Bring down the minus. We have a constant of 6, comes along for the ride. We integrate x squared, which is x cubed, over 3. Now, in the previous types of problems that you've dealt with, you would have a plus c. There is no plus c in a definite integral. We're not trying to find an equation as our endgame. We're trying to find an area, which means this has changed. So instead of having a plus c, instead you write an evaluate bar and you just bring the numbers a and b over to where you're going. Okay, so what is this saying? This is saying evaluate the antiderivative from 0 to 10. Okay, let's do a little simplifying. So this will be 30x squared minus 2x cubed. Actually, let's give myself some space here, over here. This is going to be 30x squared, again, minus 2x cubed, evaluated from 0 to 10. Okay, so we have completed the second step. So we went from here to here, and now we are done with this step of the process. So now we have to go from here to here. So what does that look like? It looks like now we're going to take this, we're going to plug in b first, then we're going to take and plug in a, and then we're going to subtract whatever we get. So what does that look like? So I'm going to use parentheses here. We first are going to put in b, which is the upper value, and by the way, the largest value. So we're going to do 30 times 10 squared minus 2 times 10 cubed. Then we subtract the same exact scenario, but plugging in 0. Okay, so what is this? So basically, I'm going to write underneath the step of the process. So this was here, basically a to b of f of x dx, right? This step here is capital F of x from a to b. This step is capital F of b minus capital F of a. So in blue, you can see the entire process from start to finish of what you must do in every single definite integral evaluation. This is what you have to go through the process of doing. So the rest of this is just the calculator work. That's it. So what do we end up getting for these values? So this is going to be 3,000 minus 2,000. And luckily, this entire thing is just going to be 0. So we can just leave it as that. So if we do the final math, we are going to get an area of 1,000 for our, and to be clear, this is our exact net area. Okay, so this right here is going to end up being 1,000 area, and you don't need a label. It's a sort of an exception, even though we are talking about area. It's an exception in calculus that when you're finding integrals, that you can just write the result, just because it will get very repetitive writing units. So basically, we found an area of 1,000. Now that's a very large amount of area, by the way. But the reason why that's a very large amount of area is because of the y-axis. You can see that this is scaled and is actually a gigantic graph. So this is actually, in the real world, if this was also 2 to 10 or 0 to 10 like this is, then this graph would be a mile up the page, hence why there's so much area underneath this curve. So just to reiterate, what's the difference between an indefinite and a definite integral? The indefinite integral is aimed in finding the full antiderivative of the function plus c, whereas a definite integral's goal is to find the area under the curve. Okay, let's do another. Number 2. So again, we have a curve. It's x squared times the quantity 3 minus 4x. Ideally, right away, we want to distribute and get 3x squared minus 4x cubed, so that we can actually do our power rule process. So that is going to be the curve that's in the picture here. And our goal is once again to find the area under this curve from -4 to -1. All right. So worth noting that this was on the right side of the axis, whereas this is on the left side of the axis. So let's see if that actually changes our answer. Let's see. Okay, so again, what's the next step in the process? We need to find the antiderivative of the function. So the 3 comes along for the ride. We take the antiderivative of x squared, which is x cubed over 3, minus 4 comes along for the ride, and we get x to the 4th over 4. This should be pretty straightforward for you now. And then we evaluate from -4 to -1. Okay, we just simplify. We get x cubed minus x to the 4th. That was a great simplifying process. Made life easier for us. And we bring down the same limits of integration, -4 and -1. So this time there's no zeros, so there's going to be a little bit more work to be had. So what do? We plug all of these numbers into the function. So we start with -1 cubed minus -1 to the 4th. So that is our highest value on the graph, so the top value, b. And then we do the same thing for -4. So -4 cubed minus -4 to the 4th. Okay, so again, this is essentially going to be your f of b minus f of a calculation, right? Whereas this is your f of x from a to b scenario down here, okay? So all that's left is calculations, and I'm just going to point out here that, believe it or not, students after the first, doing several of these problems literally just fly through this step and fly through this step and all of that, right? So, but for whatever reason, they get to the math step, the step that they've known forever, just calculator work, and they just get absolutely blown up by the negative signs and the parentheses and the odd and even exponents. You just have to really avoid doing that because that's something you don't want to be losing points on. So -1 cubed is -1 minus -1 to the 4th, which is 1, minus, again, -4 cubed is going to be -64, minus -4 to the 4th, which is positive 256. Basically what you're going to get is you're going to get -2 minus a -320, which is going to end up being just a positive 318. So it's actually interesting. You probably thought with all these negative signs that we were going to end up with a negative answer, but we end up with a positive answer. So it's a good place to sort of make a few points about this. So first of all, what I was stating before about this is, so all the area was on the right side of the graph here. All the area is on the left side of the graph. So what is that? Does it have any bearing whatsoever on the type of area that you get? No. So maybe you thought there would be a negative area in number 2. Absolutely not. Why? Because what did we say about area that's above the x-axis? It's positive. So basically all of this area and all of this area up here, it's entirely positive area. And by the way, again, this scale is crazy, which means that's why we're getting another large area going on over here. So what are we looking forward to eventually is we're looking forward to area that will be below the curve and how it affects everything, which is what we're going to be leading into in the next problem here. Okay, so trig, why not, right? Let's get going on all the different types of antiderivatives, and I'm giving you everything. I'm going to throw the kitchen sink at you in this lesson because you need to know this stuff inside and out before doing anything for the last 3 or 4 sections. Basically, it will be pointless even doing them if you don't know how to do these problems. So, how are we going here? First step, we want to find the antiderivative. Now remember, technically we can rewrite this as 3 times the antiderivative integration 0 to 2 pi of sine x dx. So the 3 can just come along from the ride as a constant away from everything else. Okay, so let's do that. So we're going to find so first 3, and then we need to find the antiderivative of sine. Okay, so what is the antiderivative of sine? Well, is there any way to get a direct derivative of sine? There isn't. When we take the derivative of cosine, we get negative sine, which means if I need to go back from sine, I'm going to get negative cosine. And again, I need to evaluate that from 0 to 2 pi. Ideally, what we want to do is we always want to keep the constant out of it. And basically, this negative here also becomes part of the constant. So we have negative 3, and then we're going to have cosine x from 0 to 2 pi. So there's a couple ways to actually do this, but I suggest doing the following. So when you evaluate this, keep the negative 3 out of here, and then just put a square bracket. And then just evaluate this function from 0 to 2 pi. So how do you do that? You do cosine of 2 pi, plug in the 2 pi first, minus cosine of 0, plug in the 0 second. So instead of doing negative 3, by the way, just to be clear, you could have done negative 3, so I'm going to put it over here. You could have done negative 3 cosine 2 pi minus negative 3 cosine 0. Okay, that is legal. And if you look at this over here, it's the same thing. But what I find is the more stuff, the more constants, the more sort of extra values that are over there, the more students get messed up. So why not remove that from the process and just take out every constant you can and leave it in the front here. So what are we going to get? We're going to get negative 3, and then we'll do a little mini math here. So 0 and 2 pi, by the way, are the same thing. So 0 is over here, but if you go all the way around again, that's the same as 2 pi. So these two values are going to be identical, and no matter what they are, if you're subtracting them, you're going to get 0. It turns out, though, they are cosines, so they're both 0. And you end up with negative 3 times 0, which is, strangely enough, 0. But is that strange, folks? Look at our picture, right? So, in the sine curve, we basically start, when we go from 0 to pi, we have that much area. But that area is positive. Then, once we go past pi, we go below the axis. And we accumulate this area, which we know very well is negative. Doesn't it look like these are perfectly symmetric? They do, which means they cancel each other out, and you get, ta-da, a net area of 0. Okay, next problem. It says, take the area under the curve 2 over x squared minus 4 from 1/2 to 2. So before I start the problem, let's do something a little bit different here. So if you look at this graph, what kind of net area are you expecting? Positive or negative? So I usually ask this in class, and by this time most students are overwhelmingly screaming negative at me. Why? Because you can clearly see from the graph the majority of the area is below the x-axis, which means that is going to basically overwhelm the positive area, and you're going to get a negative net area. So again, you're not going to see this on an exam street. You're not going to see the graph, but it's actually an incredible, powerful way to learn the material, to look at the graph and go, oh, wait, I'm probably going to get a net area here. Pretty cool. Let's see how it goes. So that's exactly what we're going to do. So a small point here. So we do have our function, but when we have 2 over x to a power that's not 1, we don't really know how to have any special rule for that. So what do? This should be pretty much burned into your brains at this point. We have to turn that to 2x to the negative 2. So basically our function now is going to be this. All right? So our next step, find the antiderivative of that. So what is the antiderivative? It's going to be 2 comes along for the ride. We're going to get x to the add 1, -1 over -1 minus 4. Whenever you have a constant, all you do is plop on a single variable, and that is the integration. And you're evaluating that from 1/2, our first fractional limit, to 2. All right, so a little simplification is needed. So it looks like we're going to end up with a -2 over just x minus 4x from 1/2 to 2 again. Now you have some options here. If you'd like to, you can take out a constant, and that's perfectly fine. I tend to take out constants more when it's already there, like there's a perfect value, whereas here we could, let's say, take out a -2 and get 1 over x plus 2x if we wanted to. That's fine, but it's not necessary to do that, so why don't we do one where we don't do that? So how do we evaluate? So we're going to plug in 2 first into our function. Then we're going to subtract, plugging in 1/2 into our function. All right, just like that. So what kind of values do we get? Why don't we do a little mini math here? So we're going to end up with -1 minus, looks like 8. We're going to have a -4 here, a minus a 2. So if we do the math, it looks like we're going to get -9 minus a -6. So if you do double negative makes a positive, we're going to end up with an area of -3. So indeed, we have found a negative net area. Now you might look at this and go, why is the number so small? For these guys, we had gigantic numbers. Well, remember, those scales were enormous, and if you look at this scale, this is only from 0 to 2, and this is just a normal scale right here, which means this is the more typical area that you find in a regular graph, something much smaller like this. So we do end up with a negative net area of -3 when we're doing this problem. Okay, so just before we get started here, I forgot to take this out. So what you're going to do is just cross this out. We're going to concentrate, even though I'm going to show you approximations, we're going to concentrate on the exact areas for the problems that we do here. So let's go to work. So for this one, we're going to do, the graph is 4 over x, and we're going to try to find the area under the curve from -1 to -3. Now, if you look at the graph, the entire graph is below the x-axis, so we are going to get a profound negative area likely, but we'll see actually how that comes together because all these graphs are sort of, grown to scale. These, it looks like the scales themselves are pretty small, so we could get something, let's say, comparable to our previous answer. Now, if we look at our function 4 over x, this is a scenario where we definitely have a constant. So if we take out a 4, keep our limits of integration, we're going to end up with this. So this is where the light bulb absolutely has to sort of flash here in your head. If you look at our previous problem, what did I state? If you have some constant over x to a power other than 1, then you need to make it a negative. Here, we have 1 over a variable to a power of 1. So what is that? What is the antiderivative of that? Right away, your brain should be absolutely screaming natural log at you. If you're not there yet, it's okay. The exam hasn't happened yet, but you have to get there. You have to be able to look at over x to the 1 and immediately know that that is the natural log. So what does that look like? So we keep our 4, as we've been doing. We take the antiderivative of 1 over x and get the natural log, and don't forget the absolute value of x, and we evaluate that from -3 to -1. So if you note here, this absolute value becomes very important. So this is a perfect example of you looking at a problem and saying, oh, Jesus, it's pretty smart that they're using absolute values here, because if I tried substituting -1 or -3 into this x without that absolute value, your calculator is going to scream at you. So what does that mean in terms of calculator code? It's going to give you an error, because you cannot take the natural log of a negative number. It doesn't exist. So in these scenarios, this is a good proof of why this absolute value must exist. In the next step, what do? We can keep the 4 in the beginning, and we can do the natural log of the absolute value of our b value minus the natural log of the absolute value of our a value, and we get this. So what does this come down to? This comes down to 4 times the natural log of 1 minus the natural log of 3. One thing you might not remember, we have done it a couple times, but the natural log of 1 is an identity, and it's 0, just like the natural log of e is 1. So you're going to basically just get negative natural log of 3. So the answer to the problem is -4 natural log of 3. So if you're looking for the exact area, then this is going to be the answer. Now, if for some reason, similar to what I was writing up here, I'll write exact here. But if for some reason they ask for the approximate area, approximate area, then all you do is throw this in your calculator, and I believe you're going to get approximately -4.39. So for the purposes of what you're doing, it is actually, interesting enough, similar to the area we just got. It is negative, so that's good. But it depends on what my math lab. I mean, I like exact answers way more than approximate answers. So if it doesn't say approximate, always give me an exact one. If you're doing some type of application problem that's of these integrals, you might want an approximate, or if you want to see what the magnitude of that number is, like how much it is, then maybe that'll be useful, but stick to the exact results. But again, there's a reason why I do 4 and 5 right next to each other, because of looking at this and looking at this and knowing that they are completely different in terms of the instincts you should be using for integration. All right, so number 6, we want to find the area under the curve 8e to the 4x from -1 to 0. So you can see over here, here's your setup. Looks like we're going to get only positive area for this one. Looks like the scale's pretty small, so the area, I'm guessing, will be pretty small as well. So let's go through and make sure that you know how to do this process. So remember, the antiderivative of e to the ax. So let's just do a little bit of a review here. So the antiderivative of e to the ax dx is equal to 1 over a e to the ax plus c. Okay, this is our basic antiderivative. So remember, this value here has to, even though it continues over here, you have to include that 1 over a constant to undo essentially the derivative. So if you're going on and moving through and trying to figure this out, that's what we're doing in the beginning. So how do we do this? We get 8 coming out. So we do -1, 0, e to the 4x dx. Next, 8 stays as it's been staying, and we actually find the antiderivative. So this is going to be 1 over our a4, 1/4, e to the 4x, and we're evaluating that from -1 to 0. Okay. We can simplify and get 2 e to the 4x from -1 to 0, which means in our next step we can leave 2 on the outside, and we can do e to the 4 times 0 minus e to the 4 times -1. As we usually do, we can do a little bit of simple math here. So e to the 0, no matter what, is 1. E to the 4 to the -1 is basically just e to the -4, right? Super easy. So if we simplify this, what does it look like? It's going to be 2, 1 minus e to the -4, which is 1 over e to the 4th. Okay, so this is acceptable to me as an answer. We could also write 2 minus 2 over e to the fourth. But either way, you can't actually simplify this, which means this is your exact area. You would be done. So either one would be exact. If you're interested in the approximate, it is approximately 1.96. So as mentioned, this is a pretty tiny amount of area, but this is a really small graph, small amount of area above this graph. So when you're doing these problems, ideally exact is the way to go. Last problem of this component of examples. Why not do some trig, right? I think that would be the best thing to do. So we end up with, we're looking for the area under the curve secant 2x tangent 2x from negative pi over 6 to pi over 12. Most students will look at this and be like, oh my goodness, this looks like it's going to be crazy. But worth noting, if you look at the graph, it does appear like we are going to get some type of negative area, just because the negative area overwhelms the positive area of the graph. I gave you this problem on purpose because I can see students being very stumped by it, so I could have just given you like the sine or cosine, some individuals, but I've seen students really get confused by something like this. So let's take a look. First things first, antiderivative. So if you recall, the antiderivative of secant ax tangent ax dx is equal to secant 1 over a secant ax plus c. Okay, this should be memorized. Again, if it's not yet, get to there. Why can this be confusing? Because there's two trig functions here, so students will get a little bit like deer in headlights. But in reality, all that is right here is the derivative secant with some variation. So what are we going to do? Well, a clearly is 2, so the antiderivative is going to be 1/2 secant 2x evaluated from negative pi over 6 to positive pi over 12. Now that pi over 12 looks very intimidating. We're very familiar with pi over 6 from pre-calculus and trig, but the pi over 12, not so much. So let's see if something nice happens. So we can take this 1/2, leave it on the outside. We're going to do secant of 2 times pi over 12 minus secant of 2 times negative pi over 6. Okay, note that this negative right here, has no bearing whatsoever on this negative. So be very careful. That negative must stay inside, and you must take the secant of it. So I've seen students that will literally remove the negative and put a positive over in the middle. You cannot do that. This is not a simple, like, in parentheses negative. This is a negative radian that is inside a trig function. We cannot remove that. All right, so what else do we got here? Let's do a little mini math. So this is nice. Why? Because if you simplify this, you get pi over 6. This is also nice because if you simplify this, you get negative pi over 3. All right? So our goal is, and our next step is to actually find these values. Well, we don't usually play around with secant. Instead, we play around with cosine. So secant of pi over 6 is the same as 1 over the cosine of pi over 6. While secant of negative pi over 3 is 1 over the cosine of negative pi over 3. Alright, so now we just have to do some trig, which will be an excellent review. So let's go through the process. First of all, the cosine of any angle is always going to be equal to the x-coordinate in the unit circle. That's our first premise because we have cosine. Next, the pi over 6 family always produces a coordinate similar to root 3 over 2, 1/2. And the pi over 3 family always presents a coordinate of 1/2 root 3 over 2. Now that's give or take some positive and negative signs, of course. But in this scenario, that's the main stuff that we're going to need here. So let's go through. We got 1/2. Again, we'll keep the 1. So what is the cosine of pi over 6? Well, this is literally just this coordinate because it's pi over 6 itself, which means we need to take the x coordinate, which is root 3 over 2. So we got root 3 over 2 here. This side a little bit more in detail. Why? Because we were able to look at the unit circle and go, well, pi over 6 is in the first quadrant of all students take calculus, so it's positive. That's easy. Pi over 3 is in the fourth quadrant, so we're going backwards, negative pi over 3. Now, if you look at this, it turns out that cosine is also positive at negative pi over 3. So therefore, again, we're taking the x coordinate, which is 1/2, and it's going to be positive. Now, if that had been sine, let's say, so if we replace these cosines with sines, so a similar problem, basically, then this would have been negative in this quadrant. So just be very careful of your trig. It just so happens that this is positive because it's in quadrant 4, the negative pi over 3. So all we have to do here is do the math. And what does that look like? Well, let's keep the 1/2 for now. We're going to get, when you do 1 divided by something, you just invert it. So you get 2 over root 3. Over here, you're just going to get 2 when you invert it. And if you distribute the half, you're going to get 1 over root 3 minus 1. Okay, so in calculus, I know this sounds kind of strange, but basically in algebra and pre-calculus, it was burned into your memory that you always must rationalize the denominator. Well, believe it or not, when we get to calculus, we don't really concern ourselves much with it. So this is perfectly fine as an answer. I know that might hurt after all of that training, but this is perfectly fine as an answer, 1 over root 3 minus 1. And worth noting, if you do 1 over root 3 in the calculator, let's say, you're going to get 0.57, right? 0.577. So if you subtract 1, you're going to get negative, so this is exact. Your approximate value that you get is about negative 0.42. Okay, worth noting, which does show, obviously, that there's more area below here. So that's a nice little look at what you actually get when you're doing that problem. So just as a whole, I tried to cover so many scenarios in these problems. I tried to cover lots of functions that you might have forgot, and just to show you that you're going to get literally any of these problems in all the different types of functions. So you'll never see these problems again because I never give the same problem twice, but hopefully, unless I make a mistake, but you're basically, you have to be ready for anything, which means you have to know your antiderivative formulas. If you don't know your antiderivative formulas, you can't do this. If you can't do this, then you can't move on. So study, 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 make sure this is concrete. And what we're going to do now is we're going to move on to a different topic than what we've been covering here, but using the same type of procedures that we're using now. Okay, so the next topic is called area bounded by a region. Okay, so this is different than net area. Even though we need net area in order to find this result, the concept of an area bounded by a region, which we often call total area bounded by the region, is more about finding how much area is shaded no matter whether it's positive or negative. So for example, if you're just looking at this picture right here, so if we were to find the net area from -1 to 2, we would expect a negative answer because it appears there's more negative area than there is positive area. Okay, so that's net area in a nutshell, right? So the total area bounded by a region is going to be all the area as a whole. So we would not count this as negative area. We would count it as positive area because we want to find the total area that's shaded in that specific, under that specific curve. We don't care about whether it's negative or where it's located to make it negative. We just care about that we're finding the total area that's shaded, and that's it. So in order to accomplish this, it's very similar from when we went from displacement to distance. It's all about utilizing absolute values. So what do you need to do? It's very logical. You want to split the graph up by where it intersects the x-axis. So if we look at this graph right now, it intersects the x-axis here, here, and here. So our goal will be basically to find the area from -1 to 0 to start. That'll be the first group of net area. And then find the area from 0 to 2 second. That'll be your second group of area. Now, you'll use the net area formula to do that. When you get that net area value, this side's going to be positive and this is going to be negative. No matter what you do, you're just going to take the absolute value of every individual region you find. Obviously, that will have no effect here and a lot of effect here. And then you will add them all together. So it's exactly the same conceptual-wise as displacement to distance. You have to find where they get broken up on the graph, and then find each individual net area region, take their absolute value, and then add them all together. So as a result, we end up getting a much larger amount of work to do, because we're going to have to do multiple net area computations. We also, if we're not giving a graph, we have to know where these are actually intercepting the axis. And to be honest with you, just assuming that these are intersecting the axis at these values is not wise. You always want to check to make sure that's where they intersect them for real. It appears to be -1, 0, and 2, but we need to check that. How do we check that? Well, you guys know that anytime you're trying to find in basic algebra where a graph is intersecting the x-axis, then you must set y equal to 0. Well, what's y? It's right here, right? So you have to set your equation equal to 0. So I'm going to write x-intercepts as my first step in every problem. I need to find the x-intercepts. So it's going to be 6x cubed minus 6x squared minus 12x equals 0. Do yourself a favor. If you see a GCF, take that sucker out. You got 6x, x squared minus x minus 2. So pretty easy factoring here. We're going to get 6x, we're going to get x minus 2, and we're going to get x plus 1. Therefore, if we set all three of these equal to 0, we're going to get x is 0, x is 2, x is -1, and there you go. We have our values that we were looking for in order of -1, 0, and 2. So basically, we found the 3 points, and they are exactly as you expected them to be. Once you find those x-intercepts, the goal is right away is to split up the regions by those intercepts. So according to this, we actually have two regions, one from -1 to 0 and one from 0 to 2. I called them R1 and R2 for region 1 and region 2. That's an easy way to do it if you like, but that's going to be the way. So the best way I would suggest to do this is to simply do something like this. You would say, all right, R1 is equal to the integral of -1 to 0 of our original function, 6x cubed minus 6x squared minus 12x dx. So the goal will be basically to find this area under the curve using a typical net area definite integral. That's it. So that's what we're going to do. What does that look like? Well, we have to integrate each piece, right? So we're going to do 6x to the 4th over 4 minus 6x cubed over 3 minus 12x squared over 2. We have to evaluate that from -1 to 0. If we go ahead here and we find that area, looks like the first step, if we want it, we probably want to simplify this to make life easier for us. So let's do that. Let's simplify. We're going to get 3/2 x to the 4th. We're going to get 2x cubed, and we're going to get 6x squared, evaluated from -1 to 0. Luckily enough, we're going to get this 0 is going to plug into all of these values and we're clearly going to get just 0 for the first part. So then all we have to do is plug in -1 to the second part. So 3/2, -1 to the fourth, minus 2, -1 to the third, minus 6, -1 squared. So we end up with this as our quantity. If we do a little bit of mini math here on the side, this is going to be 3/2. This is going to be plus 2. This is going to be minus 6. If we put this all together and we find the result, we're going to get 5/2. And I'm just going to put a cloud around this so we know that this represents this area right here, 5/2. So that's unfortunately just the first step of the problem. The second step is R2. So we have to find the same exact function, 6x cubed minus 6x squared minus 12x dx. But this time we have to go from 0 to 2. So my suggestion is, if you're integrating the same function, there's no reason to go through this step again, right? Can't we just jump to this step over here with different limits? Because we already know how this simplifies. So we're going to get 3/2 x to the fourth minus 2x cubed minus 6x squared, and we're going to evaluate from 0 to 2 this time. Why? Just skip this step because that's just your work step. You already know what you're going to get. It's the same exact function. All right, so if we want to evaluate this, it looks like we're going to have 3/2 2 to the fourth minus 2 times 2 to the third minus 6 times 2 squared. And then if we plug 0 into all of these, we're going to get a big fat 0 no matter what we do. Doing the math, we'll do a little bit of the mini math over here. It looks like this is going to be 24 minus 16. Looks like minus 24 again. So in the end, we're going to end up with -16 in our cloud as our other region. So this right here is -16 worth of contribution to the area. Now, if we were to, we're just going to do an aside here. So if we wanted to find the integral from -1 to 2. So let's just say we wanted this, -1 to 2 of our function, right? I'm not going to write it out. So remember, this is the function here, this guy. If we wanted to do that right now, then the net area would literally just be 5/2 plus -16. Done. That's the net area. But that's not what we want. So, and by the way, what a lot of students will do is they'll find this area and then take the absolute value of it to find the total area. That is dead wrong. Why? Because by doing that, you're actually taking away from the negative area with its positive area, so you're not getting the full area regions that you have. So don't do that either. The key is that now to find the total area, which is our last step here, total area, you're going to take the absolute value of region 1 plus the absolute value of region 2. You're going to put that together and you're going to get positive 37/2 as your answer. That is your total area for this problem. If you want, you can do this. Absolute value of region 1 plus absolute value of region 2, just so that you have it as a formula. But realize there might be more than 2 regions. There could be 3. I'm not going to give you many more than that, because can you imagine the length of these problems? It would be highly annoying and repetitive, busy work really to go through. You might get that like a 3-1, sure, that could be okay for like a lab problem. Usually on exams I try to stick to 2, just so that it's not a crazy amount of work. But realize, as a side note, there's so many places to make mistakes in this problem. Can you imagine like muffing up like one little value somewhere and then the whole thing goes wrong? So it is very difficult for me to grade normally, but this is basically the process for which you must find the area of a region bounded. Okay, so let's try another problem like this. We'll do 2 actually, just for practice. Make sure you're good at what you're doing here, and it's even better just to do any type of definite integral practice. Let's say this time we have the function x cubed minus 1, and we're on the interval -1 to 2. Your goal is to find the area of the region bounded by the graph. So the best way to put this is like, this is the statement that is used whenever you need to find this. Sometimes it says total area in here as well, but anytime you see area of the region bounded, you know that you're trying to find the total area in the picture. All right, so if you have x cubed minus 1, just for argument's sake, let's just say that you don't actually have the picture. What would you have to do in that scenario? Well, you know you have to find the x-intercepts to start, right? Setting x cubed minus 1 equal to 0. How do you solve that? Add 1 over, take the cube root of both sides, right? Get x is equal to 1. So if you're looking at your picture right now, you know that, or actually don't even look at the picture, that's what I'm saying. Don't look at the picture. Your interval is from -1 to 2, and what this tells you right here is that you need to split up your interval with the value 1. So without even looking at the picture, you should know that now you need to go from -1 to 1, and you have to go from 1 to 2 with your definite integrals. Now, if you look at the picture real quick, you'll see that that's exactly what happens. -1 to 1 and 1 to 2. So what are you looking at when you're doing these problems is that this step is actually going to show you how to break up your interval. Do you need a graph to do that? You shouldn't need a graph to do that. You should be able to just do it without it. Now, I show you the graph so that you can see here that the areas could be a little comparable here between the two. But the key is what? First of all, let's get some variables for this. So we'll call this region 1, and this will be region 2. It makes sense that we go through that. Let's set this up. Region 1 will be the integral of the function x cubed minus 1 dx, but it will go from -1 to 1, according to our first interval right here. Region 2 is going to be the same function, because we haven't changed, but we're going to go from 1 to 2. So now all we have to do is integrate. Let's do that. We're going to do x to the third becomes x to the fourth over 4. 1 becomes just x, and we need to evaluate from -1 to 1. Same thing here, x to the fourth over 4 minus x. We have to evaluate from 1 to 2 this time. So all this is about is subbing in the values and finding what you're going to get. So this is going to be 1 subbed in to the fourth minus 1 minus -1 to the fourth over 4 minus a -1. A little sloppy. Okay, this one over here is going to be 2 to the fourth over 4 minus 2. And this is going to be, again, 1 to the fourth over 4 minus 1. Okay, if you do all of this math, what you're going to get is, for this one, you're going to get -2. Okay, for this one, you're going to get 11/4. So if you just do the math right there, at this point, we can just go ahead and you can do your own calculator work. So you're going to get -2 and 11/4. Okay, so we know that this here is -2. We know that this is 11/4. So if we want to find the total area of this picture bounded by the curve, we would have to do -2 absolute value plus 11/4 absolute value. And yes, I do realize this is not going to do anything different, but if you wanted to go to the letter of the law, you should really do that to make sure all is good. And you're going to get a total area of this whole shaded region without negatives of 19/4. Last problem. Let's say we have f of x equals cosine. If you look at this graph right now, I know there's not a significant curve to it, but you can see there's a little bit of curve right here. So we basically are doing, this is cosine. And we're going to go on the interval pi over 4 to 2 pi over 3. Again, ideally you're not going to have the graph. So if you need to find those x-intercepts, let's say, what do you need to do? You need to solve cosine x equals 0. Okay? If you recall, I gave you, I think it was a 1-4, I gave you a little trig review with some equations that you have to find. So we're trying to find the solution to cosine x equals 0 somewhere between this spectrum right now. So if you're looking at a, let's say a unit circle, we know pi over 4 is about right here, and we know 2 pi over 3 is somewhere in this quadrant over here, right? 2 pi over 3. So it doesn't really matter where you put it in here, but we're trying to find a solution that is in this spectrum right here. So how do we find that? Well, we're looking for when the x-coordinate is 0, because cosine is always the x-coordinate. So where does that happen? That actually happens at 0, 1 at the top of the graph at pi over 2. So if we were to do this on 0 to 2 pi, it would also occur at 3 pi over 2, but we only want to know how to break up this interval. So we're breaking that up for pi over 2. So what will be our intervals? Pi over 4 to pi over 2, and pi over 2 to 2 pi over 3. Again, we're going to have two regions, so we'll call this region 1 and we'll call this region 2. You can see on the graph that's exactly how it's split up, but again, what if it just gives you a problem and it doesn't give you a picture? You have to be prepared for that and be able to solve the problem without any issues. Let's try our integration. So we need to find our net area before we can find our total area. Region 1, we have to take the integration of our function cosine x from pi over 4 to pi over 2. Okay. Some students will reverse these limits, just keep track of their value. Obviously, pi over 2 is much larger than pi over 4, twice as large actually, dx. Region 2 is going to be the same cosine x dx, because we're on the same curve, but we're going from pi over 2 to 2 pi over 3. Integration. Well, what's the antiderivative of cosine? Can we get to cosine directly by taking the derivative of another function? We can. No negative involved. It's just sine. So we are evaluating sine from pi over 4 to pi over 2. And then, therefore, we're also evaluating sine down here from pi over 2 to 2 pi over 3. So let's just do that. Sine of pi over 2 minus the sine of pi over 4. Here, sine of 2 pi over 3 minus the sine of pi over 2. What do we get for these values? So really the point of me doing this with you is all about the trig, because you must remember this stuff and be able to accomplish what you're doing. So you note last time we did this, I did a cosine, so now I did a sine. I also have a pi over 4. I did this all on purpose just to get your trig sort of warmed up and understood. So again, we talked about this before, the pi over 3 family, actually before we do that, sine of any angle is always equal to the y-coordinate on the unit circle, so that's first. Any pi over 3 family is going to be the coordinate 1/2 root 3 over 2, or a variation of with negatives, and any pi over 4 family is going to be root 2 over 2, root 2 over 2. This should be burned into your head from your previous class. We also must consider all students take calculus when we're evaluating for where the function is going to be. Okay, so we start with the sine of pi over 2. Well, we already mentioned that at pi over 2, which is right here, we're actually on the axis at 0, 1. So if we take the sine of that, we take the y-coordinate, which is 1. What about pi over 4? Well, this is exactly pi over 4, which is in the first quadrant, which means we take the y-coordinate of pi over 4, which is root 2 over 2. So our first region area is 1 minus root 2 over 2. What about the sine of 2 pi over 3? Well, 2 pi over 3 is located in quadrant 2, which happens to be where sine is positive. So we're able to just take the y-coordinate, which is going to be root 3 over 2. We already know sine pi over 2 is 1, so we can continue to do that. Okay, so these are your two regions. What I would suggest for total area is to just give it to me like this. So we know that it's at the absolute value of R1 plus R2. I would just sub in those values and leave it. So the absolute value of 1 minus root 2 over 2 plus the absolute value of root 3 over 2 minus 1. Why do I say just leave it like this? Yes, there are ones here that are considered like terms and common denominators of 2, but when you take the absolute value of these, there's much more trickery involved with that. That involves swapping the components, and we don't really need to get into that, in my opinion. It's perfectly fine to just leave it like this, as is, and I'm okay with that.